All right. So today, what I'd like to talk about is a follow-up for our last episode, which was all about thermodynamics, and get into more details about the concept of entropy, which is a super fun topic that I enjoy. And what that's going to lead us to is a discussion of statistical mechanics. So breaking away from thermo that we did last time and into the more modern way of thinking about, just heat, energy, thermal energy, temperature, that kind of stuff, in terms of statistical physics, statistical mechanics, stat mech. Just to recap, last time was a discussion of thermodynamics, which we mostly framed around the concept of 5 variables: energy, pressure, volume, temperature, and entropy. And we talked about how all of the variables depend on the other variables. All of the variables are changing in some way or another, although you could put restrictions on them. And we built up the way of thinking about energy, and then also defining new things if we change our variables, being enthalpy, when we switch from like PDV to VDP, for example. We change the one that's getting the infinitesimal change. We get a new term, and that was things like enthalpy, free energy, Helmholtz free energy, and free enthalpy. And I've already forgotten what the difference was. So go back and listen and you'll remember. So I had a thought just to kind of put a bow on this. Thermo and stat mech are parts of physics that require memorization of definitions, and I absolutely hate that, and I'm terrible at it. So I think of science that requires memorization as biology. So yeah. I just my brain shuts off when it's like, just memorize that these are the things that are happening. I like Newton's second law and then derive everything from there. And that's the way I like to think of physics. Obviously, you don't do that every time you solve a problem, but it's... Unfortunately, thermo and stat mech have the problem of requiring memorization of terms, definitions.
Yeah, there's a lot of jargon that you have to suddenly know and memorize, and I feel like that's a barrier to entry for a lot of people, myself included.
Yeah.
But I think at the end of the episode last time, you talked about the guys someone's Punnett square, essentially, basically, right? Where and that's kind of, if you don't remember, you can make one of those for yourself and have that as your permanent reference.
I would say if you're a student going through thermo or stat mech, don't be afraid to bust out the flashcard tools, because you probably haven't had to use flashcards in a very, very long time for studying, but it might be beneficial in these cases. Just an aside, when I took the physics GRE, there was a couple things that I knew I didn't have in my brain very well. I couldn't do that. I couldn't derive them from something. So I literally just, the 30 minutes before walking into the test, sat there and memorized 2 pages of stuff. I'm just okay, I know I'm not going to remember this otherwise. I'm literally just going to put it in my brain for the next 2 hours as I sit down for this test. And then it's probably going to be gone. And sure enough, it was gone, but I did answer the questions about them fine. So it worked. So no shame.
Yeah. And to be fair, I think, if you really need to know those equations for your daily life outside of being a student and being in a class, you will memorize them just by repetition, by the habit of having to use them all the time. And there's no shame in not remembering them, 2 weeks after you've learned them, if you're never using them again, that, as long as you can go back to it and look it up and make sense of it, that's the important thing. That's what we want people to learn in physics, is to be able to take something and pick up with it and make sense of it further down the line.
Right. Yeah. And I think the important concept to take away from what we talked about last time with those other energy type things is that it's a change of variables to make it more useful in certain situations. That's kind of it. You're taking energy, you're subtracting off a product of 2 variables, doing some calculus, and you get a new term, which is useful sometimes. So that's that. I mean, actually, when I was prepping for what we were talking about last time, I was like, oh, that makes sense. I get that. What is which one, and what do you subtract when, and how do they work? It's gone. I already forgot it, and it was 2 weeks ago. So yeah. And I could probably bring it up and be like, oh yeah, remember it in a couple seconds. So that's always good. Okay. So today, entropy, focusing in on the S in those 5 variables. And we're going to bring in some new concepts that are outside of thermodynamics. And then when we want to relate them back to what's happening thermodynamically, we're going to have to make some definitions. What I mean by that is some stuff is going to seem very arbitrary, but it's because we're defining things in a way that needs to be able to be related back to the thermodynamics version of them at some point. So we do have to like kind of constrain our concepts. You might be like, where did this log come from? Why is log showing up in this function? It's because we have to bring it back to thermo at some point in some situations. So last time, macroscopic properties of a system of, let's say, a gas in a box, or like, just looking around your room, draw a little bubble around some gas particles and say, okay, this is my system. I'm looking at it. It has values for energy, pressure, volume, temperature, entropy. Don't know what they are, but they're there. Now we want to dig in and say, okay, what's happening in the molecules? Let's pay attention to the underlying physics of the little stuff inside of the system. And so what StatMech is, it's a way of looking at a whole bunch of things, counting them up and saying, okay, how likely is it to be in this situation? And then we want to quantify probabilities of gas particles having certain energies and things like that, and like arrangements of energies, and then build up into the macroscopic thermodynamic properties from there. So that's really the job of StatMech, is to not take a step back, but take a step forward and dig into the little tiny things that are causing these macroscopic properties that we call pressure of a system of gas. That's the job of StatMech, and it ends up being extremely useful in situations that aren't gases and talking about pressures. When we get into quantum mechanics, when we get into information theory, cryptography, and then when we get into tying those two things together, like quantum computing, the concepts of StatMech build to being extremely useful in some like good engineering practices and useful tools. So,
yeah, and outside of physics and engineering, I mean, StatMech is actually, I think it's responsible. I'm loosely using just StatMech, but there's a few other physics concepts here, but is responsible for physicists getting into a lot of other, we would say, like non-physics fields. Like we have biophysics as a field now, and it is very heavily dependent on our understanding and knowledge of StatMech. It's basically physicists taking StatMech and applying it to biology. Or right now at UCSB, for one of the classes that we have, we're struggling to, how do you give a lab class to students remotely in a pandemic? So we have them doing kind of some simulation data analysis type projects. And one of the things that we have them doing is modeling COVID, the spread of COVID using the SIR model. And it's actually, the mathematics behind that is essentially statistical mechanics. So it's a really useful tool outside of even just physics. It's just, it can get applied to so many different fields. And so in that regard, it's probably good to know. I don't know as well as I'd like to, but this is motivation for me to want to know it better.
Well, you brought up a question now. What is the difference between statistical mechanics and statistics? Like you said that modeling COVID stuff is like applying statistical mechanics. I would have thought it was just statistics. What's the mechanics part for that?
It's just a lot of Markov chain type events, and I'm not the expert in this. It's one of my coworkers who's really good at this. It's just my understanding is basically it's a lot of the math for how something would spread is similar to kind of how some stuff might interact in StatMech.
Okay.
You can apply the same math.
I could see how it works. Like StatMech is a lot about studying equilibrium situations, meaning like just wait long enough and what's happening is like kind of nice, not some weird fluctuation of, an unlikely situation. It's kind of like, in thermodynamics, you put a hot object and a cold object together, and eventually it'll reach equilibrium when they're both at the same temperature. StatMech is really a field about explaining why that happens on a microscopic level. And so, yeah, I could see how a spread of a virus or a disease is like that, where you just like, so you have certain rules and you rules of dynamics, and you do something like hold a match to the end of a piece of metal and watch the temperature increase along the piece of metal away from the flame, similar to like a virus starts in one location and then it spreads throughout the population in certain ways, following certain rules.
Yeah,
so yeah, I can see how that works.
Yeah, exactly. And it's kind of, it follows a similar model in how StatMech and thermo are related, in that like when Dr. Fauci or whoever is analyzing COVID, the spread of the disease, and looking at models and stuff, they're not looking at every individual who's had it and how it has spread, but they're looking at kind of these more energy, volume, pressure type variables,
the macroscopic stuff.
Yeah. And you can, but you can build to those kind of variables from modeling the spread locally.
Mm-hmm. So yeah, let's get into some basic tenets of StatMech. And I think what trips maybe students up sometimes is that they start learning definitions of things with respect to thermo. Like they're already looking ahead to thermo when it's being introduced, when they really shouldn't. There's a lot to be built upon in StatMech when you don't even talk about the concept of temperature yet. We'll get there. But to begin with, StatMech is really just talking about counting. Like fundamentally, it's a theory of counting, which is, I guess, fundamentally what statistics is. So the statistics part of statistical mechanics is saying, let's look at every possible situation in this system and ascribe probabilities to them and say, okay, how likely is it for this system to be in this situation? And let's talk about how maybe the system evolves given those probabilities. That's a lot of like jargoning way of saying, let's talk about cards. And I think I'm going to use a deck of cards a lot as the foundations for counting in the concept of entropy, and in particular poker. So if you don't know poker, I'm just going to be talking about basically having 5 cards randomly in your hand pulled from a deck. And yeah, the deck probably has 52 cards. Doesn't really matter. I want to talk about the 5 cards in your hand and talk about the entropy of those 5 cards. So entropy is related to the concept of how much you don't know. So the higher the entropy, the less you know. That's kind of like the conceptual definition. You might have heard entropies about disorder. It's kind of related, but that leads a lot to be desired in terms of definitions and a little bit too much arbitrariness in the way we think about it. So I like the concept of unknowing. How much do we not know? That's really what entropy is measuring. In other words, if a poker hand has some amount of unknowing, we don't know what the 5 cards are. How many questions do we need to ask in order to determine exactly which 5 cards you have in your hand? That's really what entropy is measuring. And that gets into like later concepts of information entropy, but it's related to thermodynamics. So you can really think about the entropy as a measure of how many questions do you need to ask in order to determine exactly which poker hand you have.
Can I ask a question?
Yeah.
So I guess when I think of entropy, my first thought goes to multiplicity of a situation. So I feel like those are roughly kind of, you're describing multiplicity.
I am.
In a particular. Okay. All right.
So
I want to make sure I'm on board.
It's exactly multiplicity, which is just like how many ways are there for this hand to exist. So like kind of like, yeah. A poker hand, if you have a royal flush, the multiplicity is 4. There's 4 ways to have a royal flush, right? It could be the hearts, the king, or the hearts, the diamonds, the clubs, and the spades. Those are the 4 ways, and that's it. That's the multiplicity of a royal flush. So entropy is directly related to that, in that it is the log of the multiplicity in the like fundamental way. This is, we talked about Boltzmann, his headstone on his grave is S. The entropy equals, what is actually the formulation on his gravestone? Is K, right?
There's a K. I think it's K.
Yeah. So S equals K log W is like what his headstone says. That's his definition of entropy. W is the multiplicity, which I used to tell my students W just stands for ways, like number of ways. So we do need the log of the multiplicity. And then the K, let's talk about K in a little bit, but let's talk about log first. Entropy from thermodynamics, we talked about there being intensive and extensive variables. Pop quiz, do you remember which one? To be fair, I did not, and I had to quickly look it up before we hit record, because that's another thing that it's just like, just make a flashcard of those things because they're going to come up over and over.
I don't, but you can hear me turn in my paper here. I have notes. I could go back through. This is why I take notes. But, what can you remind me and everyone else?
Yeah, the intensive is it doesn't depend on the size of your system. Like if you double the size of your system, the property won't change. If you have an extensive property, doubling it will cause that property to change. So things like temperature, if you take a sample of 1 million gas particles in your room, look at the temperature of them, and then all of a sudden take a sample of 2 million gas particles in your room, the temperature is not going to be different when you double your sample, right? That temperature stays the same. It's an intensive property of the material, of the system. Energy, if you doubled the number of particles you're looking at, there's now twice as many particles carrying energy. The energy of your system has doubled. It's an extensive property. Same with volume. If you count up 2 million instead of 1 million, you've now expanded your volume that you're having to count them from. Right.
Yeah, the volume one is always tricky for me because I can always imagine it compressed, but we're not imagining a change of state. So
just like look in your room and count out 2 million. How much volume does it take for you to get to 2 million? It's going to be twice what it took you to count up 1 million. Okay, entropy. This is a tricky one because it's not obvious. Is it intensive or extensive? I'll give you a hint. They have to be pairs when multiplied together in the first law of thermo.
Oh, okay. So it is an extensive one.
Because temperature is intensive, entropy has to be extensive.
Yeah. But also, I think that makes sense.
Yeah. Because, now that we know the definition is in terms of ways of doing something, you can imagine if you have twice as many particles, you should have twice as many ways. Well, so here's where the log comes from. Twice as many ways does not mean twice as much entropy. Let me take that back. Twice as many ways, twice as many particles does not mean twice as many ways. Twice as many particles, number of ways of doing something, the multiplicity of something actually is a multiplicative thing. Meaning if you go from n to 2n, you actually get W going from whatever it was before to that squared.
Yeah, I think your poker example is pretty good. I don't have the math worked out immediately, right? But if you took a 52 deck of cards and you doubled it to a 104 deck of cards, so you just have all the same. Now it's not just that. Now there are 8 ways to get a royal flush, because now you can kind of pull combinations from
both decks.
Yeah.
Yeah. So let's do a simple one with coins. How many ways can you have 2 coins flipped heads or tails? There's, you can go through them. There's 4. Head, tails, tails, heads, head, tail, tail, right? That's your 4. If you double the number of coins to 4 coins, there are 16 ways to organize your coins in heads and tails order. So we've gone from 2 coins to 4 coins. We've gone from 4 ways to 4 squared, which is 16 ways. Okay, all of that is to say that ways, multiplicity, those things I'm considering equivalent, is not an extensive property because it doesn't add together. Meaning if you take a system and then add another system of the same size, we used to talk about doubling it, the volume would just add up. That's a nice extensive property of a system. We want entropy to behave like that. We can't just use the multiplicity because when you would multiply them, because all the combinations when you multiply, when you mix the 2 systems together, end up making the thing like the old number squared, which is no good. We want like S1 plus S2 to combine to give us the new entropy. So when you have things that multiply together, in other words, when you go from 4 to 16, when you square it, we want to take the log of that. The log of that number has the very nice property that when you make your system twice as big, the number of ways gets into the log function, and now you can add them. In other words, log of A times B is equal to log A plus log B. That's exactly what we want for a property, for a thermodynamic property. So if thermo didn't exist, sure, we could use multiplicity and only think about multiplicity. If we didn't have any concept of thermodynamics, multiplicity works fine. It would just lead to extremely large numbers. But we do want to eventually tie it back down to the grounded theory that came before statistical mechanics, which is thermodynamics. And so we do want something that adds up when we make our system larger rather than being a power law or multiplying together every time with all the mix of combinations that come from combining things. So that's why we bring in the log for the entropy. So Boltzmann's headstone has S equals K log W. Boltzmann's headstone has S equals K times log multiplicity. The W is the multiplicity of our system. If we grow our system, that log makes sure that the entropies could add up. Okay, let's talk about K. And let's talk about log, actually. It's not natural log. He doesn't have ln on his headstone, right? It's just log.
Yeah, it is a log.
And there's no base. It's not like base 10, base 2. It's just log.
Yeah, he does not denote the base, so presumably right. 10. But I think I've always seen it as natural log, so I'm not sure.
Yeah, physicists like the natural log because it just makes our math easier, because a lot of the stuff we're going to come into is exponential, like base E, as we'll talk about in a bit. But do you know the rule for changing log's base? Like if you want log 10 to change into log E, do you know what to do?
Yeah, I think you multiply it by the log of the base divided by something or something like that.
You divide by like you divide by the log, basically. When you're changing to another one, you divide by the old one, and then you have the new one left over. So that K out front basically is arbitrary. We know it as Boltzmann's constant because we're used to using natural log for the entropy formula, and that K has a particular value in joules per Kelvin when you use natural log. But if you use base 10, you could have K still. It's just a different K. It's just a scaling factor. And so the base of the log doesn't really matter. It just kind of gets absorbed by the K. So yeah, he's right. Obviously, you would imagine his headstone is the correct formula. I would hope so. Somebody did their homework and put it right on their headstone. But yeah, it's some constant times the log to some base of the multiplicity. And physicists typically use log base E, natural log, and then they shuffle whatever changes of base have to happen into that K.
So yeah,
that's it.
Moral of the story, Boltzmann's own constant may have been different than what we call Boltzmann's constant now, but it doesn't really matter.
It doesn't really matter because it really is just a shift in the change of variables, a way to scale things properly. But everyone agrees that there is a constant when you're changing bases, and there's a constant, as we'll see when we talk about temperature, to change temperature into energy. And as Planck figured out when he was inventing quantum mechanics without realizing he was inventing quantum mechanics, he actually had a parameter floating around his equations, and it ended up being equal to that Planck's constant, or equal to the Boltzmann's constant, which is kind of interesting. So yeah, Planck built quantum mechanics out of this conversation about stat mech. So cool. Yeah, so that's the Boltzmann definition of entropy. S equals K log W, W being the multiplicity. Let's get back into poker and talk about not entropy, but the ways in having a hand of poker. So the problem with the usual definition of entropy being disorder is that it implies there's some predetermined decision, like some group of people got together and said, this is neat and this is messy. But a different group could have come up with different definitions of neat and messy. And same thing with poker. Somebody had to come up with, we are defining a full house as this. we are defining a flush as this. And then you could go through the cards and think about the odds of having those different hands. But let's go back to the royal flush. How many questions would it take you? Let's stick to yes/no questions, which is another way of saying we are doing some binary calculations. Yes/no is just like your computer calculating things, which is where we get into the information concept of entropy, because it's really measuring how many yes/no questions does it take to answer which hand of poker do you have. And if I just said, which hand of poker do I have? That's a huge number of possibilities, which would take a lot of yes/no questions, because I'm counting everything from the royal flush all the way down to just like gibberish nothing hands that aren't worth anything in poker. So there's just like any combination of 5 cards from a 52 card deck. I don't know the number, but it's massive. But let's say I told you, so I'm already giving you a big hint. I have a royal flush. And then how many questions would it take you
I have to figure out
which one?
I guess on average 3, I would think. If I can ask you, if I can just directly ask you, is it hearts? And you'd say yes or no. And you'd say, is it spades? Yes or no. Is it clubs? Yes or no. And based on at least my knowledge of poker, I could then figure out if you answered no to all those, it must be yes for the last one. But I don't know if that's cheating.
That would work. That would work. And that would be 3 bits, but it wouldn't be the optimal way to get it. And I can tell you the way to just answer the question. If somebody asks you, how many yes, no questions does it take? Figure out 2 to the what equals the number of ways that you could have this hand. So I have 4 possible ways to have a royal flush. So 2 to the what equals 4.
2. So there's two questions we can.
Optimally, who knows what they are, but optimally, if you could figure them out the best way possible, there are 2 questions you could ask to figure out which hand I have. Given that I said I have a royal flush. And I'll tell you
it's color first. I can tell you what
color. The color first.
And then ask. Okay.
Yeah. It's almost always, the first question in a yes/no question is think of all of them in an order, and then come up with a way to ask, like, is it in the first half? That's like your first question, just to exclude half of the possibilities. That's usually like one of the best ways to get your first question done.
Binary search algorithms. Yeah.
Yeah. Yeah. So your the royal flush, I said, I have a royal flush. Your first question is it a red royal flush? And I would say yes or no. Say I said yes, then you have one other question because you know it's red. So you only have hearts or diamonds. You just ask, is it hearts? And I said no. And then you know immediately it's the diamonds royal flush. So 2 questions to figure out which poker hand I have. So in other words, you can think of the entropy of my poker hand as being 2. I know that's not exactly right because we usually use not base 2, but we use base E for thermodynamics. And usually the possibilities is not 4. Usually it's like Avogadro's number squared, a ridiculously high number, which is why most of this stuff was really not understood or accessible in thermodynamics, because the numbers were absolutely ginormously massive and just it wasn't even conceivable that it would be countable or thought about, that it was like a way of dictating the laws of physics was counting up the ways for molecules to be arranged in your room. That seems ridiculous. So Boltzmann really was the first one to take it seriously and start thinking about counting up ways to do something, and that having a direct impact on the way that physics carries out its processes. And I should say, I think we're going to have a later episode talking about the second law in particular, and time as a concept more generally, and how things evolve in time, and why there's this second law of thermo, which we said last time was that the entropy of a closed system either stays the same if nothing's happening and is boring, it's in equilibrium with itself, or it goes up, but it can never decrease. And so we have this like weird rule that kind of sits outside of other rules, that like things always lead to entropy increasing, which is like a very one-directional law, which we don't see very often. Most of our laws, all of our other laws, are reversible. Like you can do Newton's laws forwards and backwards, they work just fine. You can do quantum mechanics forwards and backwards, the laws work just fine. Second law of thermo, though, says you can't do it backwards because we'll know that the entropy going down spontaneously, something's wrong. That's not allowed in physics. And what Boltzmann really ironed out is a reasoning behind it. Thermo just said, like, yep, that's true. We see that happen. It violates, conservation of stuff, and it leads to engines having perpetual motion if we allow that to happen. Therefore, it can't. But Boltzmann was looking at counting up ways for stuff to happen in a system. And it really just comes down to the fact that what you're looking at is a very likely situation compared to the unlikely situation, which is low entropy spontaneously happening. You're just not going to see it happen. It's just not. So that's why it's a law of thermodynamics that things lead to entropy increasing. Entropy being counting up the number of ways for something to exist I'm avoiding the technical term, but I'm going to say it anyway, in a macro state. We'll talk about that in a second. You're not going to see something jump into a low probable macro state spontaneously. Something that has a low number of ways of occurring is less likely to occur. Kind of sounds obvious now that we say it that way, right? Yeah. So that's really where second law of thermo comes from is it's unlikely for something to exist in a situation that is unlikely. It's almost like a circular logic.
Yeah. I'm presuming here that, that these probabilities, since we're talking like orders, Avogadro's number of things, we're probably imagining like the likelihood of these things being like, it could happen over like a time length longer than like the scale of the universe, the lifetime of the universe type of thing. So you might as well just say, yeah, it could happen, but it's not going to. So you might as well just discount it entirely.
It's not even like the law, like the likelihood of winning the lottery. It's like an absolutely bonkers, ridiculously low probability of something happening in a weird way that would look weird to us. Like the normal examples, like to see an egg unscramble itself and build the shell back up. Like obviously that's not how physics works. That's not how life works. Why? We can talk about the likelihood of all those atoms doing exactly that thing is just extremely low to essentially be ignorable. There's no laws of molecular motion, quantum mechanics, classical mechanics that says the particles can't do that. It's just like, what are the odds that every molecule in the egg reverses backwards and completes and rebuilds a shell? It's just zero for all intents and purposes. So thermodynamics is built on basically a practical science. It's like, yeah, it could happen, but it's not even like 1%. It's like I can't express like how low the chances that these things happen. So we just say it doesn't. It's the second law of thermo says it's not going to happen. Yes, technically there's a tiny, tiny, tiny chance, but we ignore that. It's not worth thinking about. We always see things happening in a particular sequence of events. And again, we'll talk about time, I think, in maybe the next one. I need to finish reading a book or two. But yeah, that's coming and it's related to entropy. Okay, so let's talk about poker again. What's the likelihood of having the royal flush of, I forgot what I said, diamonds, I think. If I had a diamond royal flush versus having the hand of 2 of hearts, 6 of clubs, 7 of spades, 8 of hearts, and jack of clubs. Like, which one is more likely? Which one's less likely?
I think they're equal, right?
They're equally likely. Exactly. That's an interesting point. Each 5-card hand of poker that you're dealt is exactly as likely as a different 5-card hand of poker. So why do we ascribe royal flush is extremely rare and the most valuable poker hand?
Well, because we've put in, I think part of it is we put an order to the cards, like the fact that, I mean, I guess like the highest level answer is just because we have prescribed certain value to different, orders of cards. Like for instance, we in poker we have valued having cards in order, like in numerical order, and we have added value to having cards of all the same suit type of thing. And then we also value higher numbered cards, not just straight order, but higher. So when you like combine all of those things together, then it like if you make that the requirement that you have to have not just any 5 cards, but the highest 5 cards in order that are all the same suit, then your probability is shifting.
Right. So yeah, you said it right. They have the same exact probability of happening, but we like outsiders have determined, just completely independent of the cards, that some are more valuable. What I described first, the random hand, quote unquote, and the royal flush hand, each of those are considered in StatMech microstates. So we talk about like the exact configuration of all the particles in a gas, or the exact cards in our hand, 5 cards. Each one of those is a microstate. Then we humans, come in and say, this one is a special collection of microstates. The 4 suits that make up a possible royal flush hand is a collection of microstates that has a similar enough quality that we'll say they are what we consider a macrostate. So we say royal flush macrostate. There are 4 microstates in that macrostate. Random cards that aren't worth anything in poker, that's a macrostate. I don't know how many there are. There's lots, like way more than 4. And there's no value to them. It's the most probable hand, which means it's the least valuable hands. The collection of random cards. What is the odds of getting 2 cards that are the same, different suits but the same, like a pair? That's less likely than the random cards. So we give it a value. It's like the lowest possible value, but it's a value of whatever it is. I don't know how many ways to do it. I should have done all the math for poker hands. Somebody has that memorized and they know like exactly what the odds are for that kind of stuff. But it is a different macro state than the royal flush or the random hands or the full house, which is a different macro state. So each of our labels of hands of poker are macro states. And the number of microstates that make up those macro states, that's the likelihood of being in that macro state. And the lower the likelihood of being in the macro state, the lower the entropy is. So royal flush, super low likelihood, super low entropy compared to the other ones. And I should distinguish, I'm assuming all microstates are equally probable. There's situations where that's not true. We can talk about that in a bit, but that's the general case of just, any 5 cards are equally likely compared to every other random 5 cards drawn.
Can you say the last bit again with microstates and macrostates and entropy?
The number of microstates in a macrostate, the higher the number is, the higher the entropy. And I should say entropy is a function of macrostates. It is not a function of microstates. Entropy is a function of royal flush. It's not a function of Diamond's royal flush. Gotcha.
Because, in physics, we can't tell, the difference between each individual card. We can only, a molecule or an atom of nitrogen or a molecule of nitrogen is the same for any molecule of nitrogen, right?
Exactly.
Of thing. So.
Yeah. And in StatMech, there's a quite a heavy emphasis on identical particles versus like indistinguishable particles versus distinguishable. That has a big effect on entropy and StatMech calculations. Yeah, and exactly right. Like most of the molecules and atoms we encounter in particles are indistinguishable, which is important to the calculation. It affects the multiplicity.
Yeah, because you can imagine, if you have, I'm trying to come up with a quick example off the top of my head, but if you have a bunch of nitrogen in a container somehow, you can't tell where any one nitrogen molecule is with respect to any other, which nitrogen is which, but you throw an oxygen molecule in there, and then now you have, a huge number of ways to organize that system where you can track where that oxygen molecule is. So suddenly you have a way larger multiplicity than you had before.
Yeah. And I want to emphasize the poker thing is not just like an analogy. It is precisely defined in statistical mechanics. Like what we are talking about with the entropy of a poker hand is statistical mechanics. Like it's included in that. It's not like a like little side thing that's like, oh, think of it this way. It's like, no, that's it. That is it. What it is not is the word I just said on accident, which is thermodynamics. There's no temperature to your hand of poker. It's not defined. It exists outside of thermodynamics, but it is inside statistical mechanics. So yeah, StatMech is all about counting up macro states, the microstates inside of macro states, and talking about the likelihood of being in a particular macro state. In particular with poker, yeah, the hands that are more likely are less valuable. They have a much higher entropy. Takes a lot more questions to ask to figure out which exact hand do you have. You can imagine having four of a kind. That fifth card throws in a whole bunch of different ways to have four of a kind. Never mind the different ways to have four of, which four cards.
Yeah, I mean, it takes the same number of questions as the royal flush to figure out what those four, maybe even another question. So you have to ask which card it is, I suppose. So it takes...
Yeah, you have a lot. So even if you just had four cards that are the same, never mind the fifth one, you still have, is it 13? How many cards are there? Ace through, so up to 10, and then Jack's 11, Queen 12, King 13. Yeah, so 13 cards.
Yeah, so yeah, you would do the, I don't want to go through the whole thing, but you would do like the binary search that you were just saying, is it greater than 7 or whatever, and then you narrow it down that way. So it's that optimal one. So maybe that's, I guess we know the optimal number of questions. 2 to the 13 is no. How did you figure out?
So if it's just 4 and we have to figure out which value is the 4, then yeah, it's 13. So it's 2 to the what equals 13, and it's not going to be perfect. So we need to round up, because that's the number of questions it'll take, is at least that number. So it's going to be 2 to the
4.
2 to the 4 is 16.
Yeah.
Right?
Yeah. So, okay, 16 questions. But then, yeah, that's already more complicated. And then now you added to that. Okay, now you have to figure out what out of 48 cards the other card is. And now it's just...
Right. Yeah. Yeah, so the entropy of 4 of a kind is much, much higher than the entropy of a royal flush, but it's much, much lower than the pair. So basically, people wrote poker rules based on entropy. They didn't really. That's not true. I thought of an interesting situation of identical / indistinguishable particles versus distinguishable is to think about 2 coins in heads or tails. We said that there's 4 possible ways to do that. If you have like a penny and a dime, that might change things where you're like, it's actually different states if the penny is heads up or the dime is heads up, because you have different coins now. Those are distinguishable particles. So it's a different macro state. We identify that as different if the dime is the one with the heads up than the
so like if you
penny.
if you have 2 pennies, you have one less state, right? Because you have heads, tails, but then you can't tell the difference between heads, tails, or tails, heads.
Yeah, that's a macro state, which has a multiplicity of 2. It has 2 microstates inside of it.
Yeah.
So we lose that macro states multiplicity when we bring in 2 different types of coins. Yeah. So that's when we get into like distinguishable versus indistinguishable particles, stuff like that. So what does this mean in terms of gases and thermodynamics? Look at the air molecules around you right now and consider how many ways are there for those molecules to be arranged in the room you're in or wherever you're sitting. It's absolutely ridiculously massive number, right? So that is what we're doing when we think about the entropy of gas. It's like, how many ways can we organize these molecules to be in this configuration? And what's interesting is StatMech is fundamentally a discrete math problem. There's not continuous functions. Let me say that. There are continuous functions, but we need to discretize them. We need to say, this is a state, which is separate from this state. And what we talk about in StatMech is that in phase space, the position and momentum of every particle inside of your gas system lives in a phase space that's like, draw it on a sheet of paper. It's like however many gas molecules they can be moving in the XYZ direction with XYZ momentum. Massive space. But we divide it up into little blocks. And the blocks have a finite size. And we say, how many molecules are in this block? How many are in this block? And how many are in this block? And we start counting up how many molecules have certain XYZ and momentum in XYZ directions are in each block. And that's how we literally count in statistical mechanics the likelihood of a situation to be in a certain configuration. The entropy of the gas is based on these little counting systems inside of blocks of phase space. That was a huge leap in physics jargon, but that is how we do it. And what's really interesting is the size of those blocks have dimension of, do you know actually what the size of the blocks are?
I mean, I guess if it's X times P, that's energy.
X times P is action.
Action. Oh, yeah, thinking H bar.
It is H bar. So, yeah. I mean, it's not H bar, it's H.
Oh, H, yeah.
It's Planck's constant. So that's the fundamental grid size of phase space when we're doing stat mech, is we break things down that would look otherwise continuous, like X can be anything from the left side of your room to the right side of your room, any value continuously. But we divide up X and P into little blocks that are of size, of dimension, of width, H, Planck's constant, which, I think is incredible. That's where Planck was building quantum mechanics without realizing it. He says, I need to divide up the like phase space into chunks. And that size of the chunk is what ended up being Planck's constant. Yeah. So basically, your infinite possibilities need to be chunked, discretized, countable, because everything about stat mech is counting. You're literally counting up stuff, and the numbers that we're counting are just so massive it's hard to wrap your head around. But when you get into like the nitty-gritty details, it's fundamentally you're counting stuff. Let's talk about where this ties in to temperature now. We haven't really said anything about temperature of poker hands. We've kind of talked about just gas molecules moving around. But when we want to bridge the gap between thermodynamic entropy, which we talked about as like one of the 5 or more odd numbers of variables that define our state of our gas system or whatever system, if we want to tie it back into the stat mech version of entropy, what we want to do is write out the entropy function and parameterize it. We want to get this like maximum value. Everything has to do with like equilibrium situations, and you can think about equilibrium situations in the stat mech side of states as entropy being maximized. Like if it's not maximized, the second law says it's going to keep increasing, right? And at some point it will be maximized, and that's when we say things in equilibrium. So take your stat mech version of entropy that involves counting the K log W. And actually, there's a little bit of a tweak there that we'll get to. But take that version of entropy and maximize it, and you're going to end up with a couple parameters. And the way to maximize it is something I'm not totally clear on the math-wise, but it's Lagrange multipliers. Do you remember that from like functional analysis?
Yeah, from my vector calc. It's just, I mean, my loose remembering of it is basically it's what you do in 1D, but over 2 dimensions, and it's slightly more complicated in 2 or more dimensions, because you now kind of have a surface or like a path that you have to look at, not just one parameter. And so, you kind of have to change a whole shape of them, and it's a way to make it simply. It's essentially functionally equivalent to doing one-dimensional optimization, but
yeah, like you take the derivative, set it to 0 kind of thing. Like that's how you find the maximum of some function.
I mean, I don't remember, the details of the math, but you end up with the same thing. It's the tool to do the same sort of thing. So now you're finding like an optimal path or surface or that type of thing.
Yeah. And for this, what we're doing is we're introducing a couple Lagrange multipliers. And again, sorry that we're fumbling the math details, but those parameters, those multipliers, are based on constraints, like the constraint that energy is conserved, or the energy changes in a particular way, or the number of particles behaves in a particular way. So now we're tying that entropy stuff with counting into energy and number of particles constraints. And when you build in those constraints and do the Lagrange multipliers, you find out one of the multipliers is this parameter beta. Beta ends up equaling, when you tie it back to thermodynamics, it equals 1 over the Boltzmann Boltzmann constant times temperature. Beta ends up being like an inverse temperature value. It's this parameter that floats around from Lagrange multipliers. It's a way that ties in the probabilistic entropy from StatMech into the thermodynamic stuff of entropy from thermodynamics. And the go-between ends up being a parameter beta that is 1 over Boltzmann times temperature. So that's where temperature jumps back into StatMech, is where we've got temperature when we need to relate things back to thermo, which makes sense. But StatMech, again, lives outside of thermo. It's just a whole different field, but then it can relate back when you need to using this parameter beta. Beta is usually referred to as inverse temperature, and then the Boltzmann constant's there just to get the units right. It has units of 1 over energy. Boltzmann's constant is joules per Kelvin, and then temperature you measure in Kelvin. So yeah, 1 over that ends up being inverse energy. So all that was just, relating the StatMech counting stuff of entropy into the thermoentropy. But a nice way to think about this, instead of talking about W, the multiplicity, the number of ways, another person that we talked about last time, Mr. Gibbs worked out another way of thinking about StatMech that is different than K log W, which is Boltzmann's work. Gibbs brought in the concept of probability. Nothing in Boltzmann's work. Well, Boltzmann did do this also, but Gibbs gets the credit for working out the entropy in terms of P, the probability of being in a particular, I want to say macro state, but now I'm balking and wondering if it's micro state. I think it's macro state. I think it has to be macro state. And the reason I'm going to step back. It's microstate. P is the probability of being in a particular microstate. And for a deck of, or a hand of poker, 5 cards, all of them are equal. But the entropy of a macrostate is to add up all the probabilities of the microstates of that macrostate in a particular way. And it looks very similar to Boltzmann. What Gibbs entropy looks like is the sum. Actually, it's the negative sum. We'll talk about why it's negative in a second. Of K times the probability of a microstate being the system being in that microstate times the log of that probability. So let's just focus on what's happening on the inside of all that stuff. Probability times the log of the probability. That is Gibbs' contribution to this entropy discussion in StatMech. So the log of a probabilities run from 0 to 100%. In other words, from 0 to 1. What's the log of a number less than 1? Is it positive or negative?
Less than 1, it's negative.
Yeah. So we have a negative number because the log of probability is going to be negative. There's a negative out front of all that to bring it back positive, so the entropy is a nice positive number. But he's adding up the probability times the log of the probability for every microstate in your macro state. So now we're dealing with situations where it's not just the number of ways like Boltzmann was counting, but the ways have different likelihoods. It would be like a royal flush of clubs is less likely than a royal flush of spades. We've freed up the ability to change that possibility, it adds a bit of complication, but it's more general. And it's in particular important with thermodynamics when we're talking about temperature, because the higher the temperature, the better chance you have of your system being in a higher energy configuration. that temperature affects what's accessible to your state, to your system, to your state. So Gibbs bringing in the possibility that probabilities vary for different microstates. The probability, we're going to bring it back to Boltzmann. The probability has a nice functional form, and it has to do with that beta, which is why I talked about it a second ago. Do you know the Boltzmann factor for the likelihood of a state of a particular energy E? Do you remember doing that stuff?
Is that the, like, it's in my head, but no, I mean, my guess is, for some reason, I'm thinking of like the free was not modes, but why can't I think of the word? I'm almost imagining like the dimensions of motion, like whether it can vibrate, rotate.
Oh, degrees of freedom?
Yes, thank you. Is it the degrees of freedom times beta? I don't remember. Is the right answer?
No, it's not that. I was kind of hesitating because it's kind of related to that, but it's not. What we're looking for, I'll be Alex Trebek, rest in peace. No, the answer we were looking for is what are exponential functions? It's if we had a guess at the likelihood of a state being occupied, the likelihood of our system being in a particular state of energy E, we could imagine that the higher the energy is, the less likely it's going to be in that state. It's just inaccessible if it's like some crazy, ridiculous high energy state. And I'm talking about like particles whizzing around super, super fast, all of them at this like crazy high energy situation. We're generally not going to experience that in a room of gas. So what we have is something that starts off high, but then trails off to lower and lower likelihoods as the energy of the microstate increases. So the Boltzmann factor is kind of like the probability in Gibbs, but we're going to talk about a fix for that in a second. The Boltzmann factor is E raised to the negative beta times the energy of that state. So as the energy goes up, the likelihood, the Boltzmann factor, goes down. Does that make sense?
Yes.
That beta in front of the energy, remember, is inverse temperature. So the higher the temperature, the lower beta is. So if the temperature is really, really high, beta is really, really small, E to the really, really small number, is that big or small?
Oh, gosh.
E to the negative really, really small number.
Yeah, so it's 1 over E to the small something. So I think it's small, super small, or big.
It's super big.
Big,
so,
yeah. 1 over it is the one that got me.
Yeah. There's the 1 over. That minus sign out front is important. It's like 1 over E to the beta E. 1 over E to the beta energy. What I want to say, all that reasoning was to say that the temperature being higher means that the high energy state is more likely to be occupied, which also makes sense, right? If your temperature is high, you have a lot of particles whizzing around really fast. That state of your gas system is in a high energy state. It's likely to be in a high energy state. It opens up the ability to be in a high energy state. That's what that Boltzmann factor is. I'm calling it a Boltzmann factor. Boltzmann factor is the E to the minus beta energy.
Yeah,
that's what.
Sorry, I was gonna say it'd be weird if you opened your oven, and pull out some cold pizza that you expect it to be your pizza to be at a high energy state. You don't expect it to be cold.
Right. Yeah. Okay. So that's the Boltzmann factor, which is almost the probability in Gibbs's entropy equation, but we need to take care of one last thing, which is that all the probabilities need to add up to 100%, or they need to add up to 1. If you've done quantum mechanics, you're familiar with normalizing your wave functions, where basically you're saying the same thing. All the probabilities, the state is somewhere. It has 100% chance of existing. So we need to add up the likelihood of it existing in each individual state. All those probabilities, all those factors add up to 1. So the probability isn't just the exponential, that Boltzmann factor. It's add up all the exponentials, and then say 1 over that sum of all the exponential factors. is the normalizing thing. So the probability of being in the ith, like a little index number that we would use for counting, the probability of being in the ith state is the Boltzmann factor divided by the sum of all the Boltzmann factors. In other words, we need to normalize it. That's how we get the actual probability.
Yeah, just to relate that back to something more tangible, that's like saying the odds of getting a particular number on a n-sided die is 1 over the number of sides of your die. You got to normalize it.
Yeah. So like an odds of a 1 is 1 in 6, and odds of a 3 is 1 in 6, and we have 6 sides. So yeah, 1 6 plus 1 6 plus 1 6 plus whatever 6 times, those add up to 6 6, which is 1. That's like a nice normalizing term. So the sum of all those exponential Boltzmann factors for each state, the likelihood of that state being populated, the weighting factor, you can think of it. That sum has a special name, and it's one of those flashcard terms. You're like, wait, what is that thing? It's the partition function. Have you heard that term?
Yeah. I've heard, there's the partition function, the equipartition function, and for some reason, I don't know why, but grand canonical ensemble is coming to mind as well.
Yes, there's different partition functions for which canonical ensemble you're in. So the typical one is that sum of all the Boltzmann terms. The way I think, so in that sense, the simple partition function is just like the normalization factor. It has no other special meaning. Well, it does, but it can be thought of as the same thing as your quantum mechanics normalizing factor. We're like, oh, this isn't normalized. I need to make sure it's normalized. Just bring in this other factor. Usually it's like a squared when you're doing a wave function. That's what the partition function is. It's a normalization factor to make sure your probabilities add up to 1. The way I think of it for like poker, what I said before is that every 5-card hand, the random hand and the royal flush are equally likely. The royal flush of exactly clubs, that one is as likely as the particular random hand that I rattled off a while ago. Each 5-card hand is equally likely. What we do is we decide the partition function, and we say, okay, this set of microstates is a distinct macrostate. We're going to partition it off from the other hand of poker, which is 4 of a kind, which is these collections of microstates, which is different than the hands that have pairs in them. That's a different microstate. So we are like, maybe I'm using this term incorrectly, a priori partitioning out the microstates into their macrostates. That's what we're saying. That's kind of how I think of the partition function, but it's a mathematical one in that exponential Boltzmann term that depends on temperature and energy of the states. But it's the same thing, as though we would organize the hands of the 5-card hands possible, put them all in a big row, and then put partitions down every so often and say, okay, these are worthless. These are pairs. These are 3 of a kind. These are 2 pairs. These are royal flushes. These are full houses, that kind of stuff. We just drop down partitions. Yeah,
and then the when you combine all of those, all hands in poker, that's when you get back to, that's your normalizing factor. It's like, okay, you put it, when you put each partition, you break it up however you'd like, and you put it all back together, then you're back to, okay, that's our whole set. That's everything.
Yep. Yeah. So yeah, that's the partition function. So let's talk about the funny term. I think I said it last time and I said it incorrectly. The canonical ensemble, the grand canonical ensemble, micro canonical ensemble. This is another one of those, just make flashcards because you're going to forget what they mean. And it really comes down to which variables are you allowing to vary and which ones are being held constant. So, and you can imagine micro canonical ensemble is like the most restrictive, locked down, quote unquote, simplest, which is sometimes considered, sometimes they're nice and they label these ensembles with what variables are being held constant. So micro, I had to look at my notes, NVE are constant, the number of particles, the volume, and the energy. And here's where it gets tricky, because it sounds like, yeah, that's super simple. That's like the sealed box of particles, nice and easy, no energy in or out, nice and insulated. The problem is the temperature is not well defined. You can think of that like as the poker hands. Like, what's the temperature of the poker hands? It's not defined at all. It doesn't have any meaning. There are some things that are analogous to temperature in other situations where you could work out something that looks like temperature, but it could be ambiguous what your temperature is. You have to be careful. So by making restrictions, it seems simple. It is simple mostly, except when you try and bring in some macroscopic properties that might not be well defined in that ensemble. So be careful. But yeah, N, V, G are constant, which doesn't mean everything can change, meaning temperature may or may not be changing, but it's just not well defined. That's the micro. The canonical ensemble, that's NVT, are constant. Number of particles, volume, temperature, nice and constant, but your energy can change. This is, if you've done StatMech at all, you've probably had experience with spins and magnets and stuff like that. That's a nice way to count stuff because it's like heads of coins, like heads and tails, flipping coins. Magnets are like spin up, spin down particles. You can do a lot of like math that's not too complicated with spin up, spin down particles in a grid or in a chain. So what I'm dancing around is the term an icing model for magnetism. That's your canonical ensemble, meaning the number of particles isn't changing, the volume's not changing, the temperature's not changing, but your energy can change because your magnets can flip up and down. And so when something spins from down to up, we could say the energy increased. So we count up how many up magnets, how many up spins there are in the magnet. And that's usually that's modeled as an icing model. And then the grand canonical ensemble, that allows N to change, but we usually talk about the chemical potential being constant at a given N. So we have mu VT is the grand canonical ensemble. The constant things are the chemical potential, the volume, and the temperature. So the number of particles and the energy can change in the grand canonical ensemble. Whew. Get your flashcards out.
Yeah. So if we want to go up a level, and let's not, like if we reduce restrictions at some point, have we created more and more names for like what comes above grand?
I think you look at what is constant and you put ISO in front of it, and you're just like, this is the isovolumetric ensemble, and you're just like, okay, the only thing that's being held constant is volume. Everything else can move. That kind of stuff.
That's not as fun. They should have said like, this is the ultra canonical ensemble. This is the super mega,
super max mega ultra. Yeah. And they do have different partition functions because different variables can contribute to like how you partition the microstates into their macro states. So yeah, that's StatMech in a sense. I think it's nice to overview our different entropy terms. We had thermo from last time, which was part of our first law with like energy being PdV and TdS. Sometimes it's talked about as like a heat over temperature. Maybe some people don't like that. It's not well defined. We did talk about the weird cycles last time of the thermodynamic entropy calculations from like the 1800s. By the way, you talked about Carnot. Who did you see a gravesite for?
Both of them. I did see. Oh. Well, I saw Carnot and I saw Boltzmann. Carnot's in Paris, Boltzmann in Austria. But the thing that happened is I took a picture with the wrong Carnot because there's multiple Carnots buried at the spot.
When I was looking this up, I was like, when did entropy first come about? And it was like, oh, Carnot, like early 1800s. I'm like, cool. And then it's like, his son, the second Carnot, did more. I'm like, oh, okay, there are more than one Carnot, and they worked on the same stuff. So yeah, you saw one of them. So that's the thermoentropy, which is all about heat and temperature and energy and stuff like that. Boltzmann came along and started talking about counting ways to do something, the multiplicity, with his headstone equation S equals K log W. Gibbs then talked more about the probabilities, not just counting up stuff, but how likely are things to be in certain microstates, and organized them and talked about the entropy of a macrostate dependent on the probabilities of each microstate, which is almost always the useful formula to think about. So you're going to add up a whole bunch of probabilities times the log of the probability. And you got a minus sign to make sure it's positive, and probably a K floating around to get the units right. There's one more after that, and it looks almost identical, but it's Shannon entropy, which is all about the information entropy. And conceptually, there's some distinctions between Shannon entropy and what we could say is Gibbs entropy. Shannon entropy is the same formula, negative sum of probability times the log of the probability. He doesn't have to worry about the constant K floating around, but conceptually it's slightly different. Boltzmann and Gibbs were talking about microstates and how many microstates make up a macrostate. What's the probability of the microstates? That kind of stuff. Shannon was talking about like what we would probably think of just variables, and really he's an engineer thinking about information theory carried in a signal. So he's talking about like signal processing and how much information is there in a certain amount of distributed, a signal being sent to somebody. So yeah, his stuff is more about the probability that some random variable has a particular value, which is kind of like how we were talking about like the cards. I mean, I guess all of our stuff about cards was information, Shannon entropy, and relating it back to the thermodynamic stuff through Boltzmann and Gibbs. So I don't know. It's interesting. Shannon was pretty late, like in the 50s, where he added to our understanding of entropy. I guess it's worth noting that he likes to use log base 2 because he's talking about computers, information theory, binary information. So his calculations are all log base 2. Not that that matters that much, but it's a nice little addendum to his contribution.
I was. You said Shannon. I'm like, where do I know Shannon? Shannon. And then I remembered I know him from the Nyquist-Shannon sampling theorem, which is, I think it's basically that theorem that says you need to have, like, in order to rebuild a periodic signal correctly, you need to sample at like half the rate of the signal. Something like that. But
so you need like two samples, two like checks, like per oscillation, if it's like a wave or something like that, to distinguish. Yeah. They use that in like astronomy too. Like they talk about like digital photos, like what's the resolution have to be to determine how far apart two stars are, that kind of stuff, or to distinguish that it's actually two stars and not one blob of light. And you talk about it with like Airy functions. I kind of remember doing that kind of stuff in optics. But yeah, it's like, yeah, when you start digitizing things, then Shannon information entropy and the Nyquist theorem pops up. All of this, by the way, is making some assumptions about the ways probabilities relate to each other. There is a whole nother field that builds on this where probabilities are dependent on each other. And it gets very messy very fast. That is getting into density functions of probability, where you have like a probability matrix. Everything we're doing is basically the diagonal elements of a density matrix of probabilities, but there's certainly in why can't I think of this term? Quantum computing. You have often diagonal elements of a probability matrix that are very important because things are correlated and you have entangled systems carrying information, and it gets way messier. So have fun if you would like to get into quantum computing, but it's a lot of this stuff, but we're making some assumptions that like no one in their right mind would think would be even important until we started doing quantum computing. And we're like, wait a minute, this matters now. These weird things that used to not matter at all are now very important and determine a lot of stuff about us, about how this stuff works. So, yeah. Good stuff. I really like entropy. I like thinking about entropy, and I'm excited to talk about the second law and quote unquote the arrow of time more and how they relate. We might have touched on most everything, but I'd like to dig into it more. I'm reading Sean Carroll's book that's titled, I can't remember it. I'm reading Sean Carroll's book called From Eternity to Here. I believe that's what it's called, which is a lot about the arrow of time.
Which I think is that Brian Greene book or someone's book?
No, Sean Carroll.
Oh, he also wrote Arrow of Time?
Oh, is there? So when I looked up Arrow of Time as a book title, because I think I said that last time, I want to read Arrow of Time. It was like a book that's pretty old that I hadn't heard of. But then I was like, no, Sean Carroll's book, and it's called From Here to Eternity.
Oh, I see. I thought maybe it's just used so much, the Arrow of Time as a thing. But I thought there was a book as well called The Arrow of Time.
I thought so too. And I thought it was Sean Carroll. But he just gives talks a lot. And he has blog posts and YouTube videos talking about the concept called The Arrow of Time. But his book is not called The Arrow of Time. So okay. I think the marketing team missed a mark on that one, that there's some confusion in branding. Maybe there's another book called Arrow of Time, but I'm reading From Eternity to Here by Sean Carroll.
This was actually really helpful for me as I'm kind of wondering. I think I'm a little wrong in thinking this, but I almost feel like I heard this prior to learning StatMech. It might be one of those cases where it's actually more like a Feynman thing for me, where it's like, the Feynman lectures where you're a lot easier to understand once you already know all this stuff. Mm-hmm. But this was like, I was like, oh, okay, yeah, these are all making sense. This is a good refresher. Like, oh, here's kind of an explanation for some of those things that I remember talking about, but could not grasp in terms of conceptually what it was at the time.
Yeah, I think there's, like we said at the beginning, there's a lot of vocab, like microstate, macrostate, blah, 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 like whatever, on partition functions, those kinds of things just fly in one ear out the other, and you do math with them and then they're lost conceptually. But yeah, I like thinking about the fact that entropy exists in StatMech before we even get to thermo, and I start losing grasp of what's happening once thermo touches the StatMech. I start losing it quickly because I think it's like we historically learned thermo first. And so we're trying to fit StatMech principles into thermo principles, and it gets messy quickly. I've heard that beta, if we didn't know thermodynamics, our concept of beta being the inverse temperature would have been a better definition of temperature. It would have saved us a lot of trouble in defining things. If we would have just used beta, basically we would use a measure of how cold something is as it increases in value rather than how hot something is. Similarly, absolute zero is beta going to infinity, which is unreachable, which makes sense. But temperature just having a hard limit at zero is kind of strange. So, yeah. I like thinking about cards and the concept of unknowing. The disorder one always threw me off because it seemed very arbitrary. Like I was saying, it's equally likely to hold a hand of random cards as it is to have a royal flush. Those are the same likelihoods. Same with, it's equally likely to have a room in a particular messy state as it is to be in a particular unmessy state. But we come in and partition off the messy states and say, all of these were scattered clothes in your room states are collectively the messy states. Whereas this one particular organized room state is the unmessy state. So we have an arbitrariness to that definition, which is fine when you talk about StatMech and microstates and saying ahead of time, these are distinct. These are different.
Yeah, I think I was always confused by that as well. And I kind of feel like maybe in pop culture, it might be better just to drop that and start talking about poker hands as a way to explain it. But I think maybe I'm wrong here, but I think the reason behind it is just that, if you imagine, if you say a wine glass is ordered and a broken wine glass is disordered. Those two things make immediate sense to people. And there's a lot more ways to like organize a broken wine glass than a wine glass. But like, yeah, I think it tends to kind of lead to weird thoughts about like people just take it very loosely, and then they end up kind of down these rabbit holes with wrong assumptions about what entropy is or what entropy means.
Yeah. The website we talked about last time, Aviatin, the John Denker website, there's a lot of information there about entropy and misconceptions, and he very much avoids the disorder definition of entropy, analogy of entropy. And he really emphasizes that entropy is a measurement of how much you don't know about something, which brought up some more questions in my head of, it seems very not relativistic in like Einstein relativity way, but like if you know that I have, like you're playing poker next to me and you see a king of hearts, you see one card, king of hearts, you have fewer questions to ask about what's in my hand than somebody who doesn't know any of my cards, right? So in that sense, the entropy is different for you than it is for somebody else, which he has a whole page about, saying that's fine. That doesn't break physics. Entropy is a relative amount of knowledge of a situation. And he talks about how magic tricks they take advantage of that, in that it seems like the person who the trick is being played upon is that person thinks all possibilities are equally likely, but the magician has forced, by knowing something ahead of time, has forced the entropy to be lower than we think. And so that's essentially the magic. It's like the entropy for the deck of cards is actually lower than you think it is as the person who's getting the trick played on them.
I like that.
Yeah.
Explanation for all of magic is entropy.
Yeah. It's a sleight of entropy hand. Yeah. But yeah, it's I like thinking about entropy in that sense. Like, how many questions do you need to ask to get to the exact hand? But the important part was, in that very beginning, I said I have a royal flush, and so that dropped the number of questions to 4. Or I forgot what it was, 2 questions. The possibilities down to 4 questions to 2. But that was to emphasize that the entropy is a function of the macro state. It's a function of royal flushes. If we didn't know that, the macro state, before you know that I have a royal flush, is all the possibilities open to my hand of 5 cards. That's the huge total collection of microstates, which is a much higher entropy. Cool. Yeah, I always enjoy relearning about entropy, relearning about the vocab involved. But yeah, I would say if you're a student, don't be ashamed to make flashcards at this point in your career. You probably haven't had to make flashcards in a very long time. Now's the time to do it.
And don't be ashamed to have forgotten it and to go look it up again.
Right.
Again and again.
Yep. Totally. All right. So next time, talking about entropy and the arrow of time and tying into some cosmology stuff.
Cool. Awesome. Looking forward to it.
So we were pretty bad about outros, but yeah, we have a subreddit. You can come say hi at r/thehyperfine. And I do have an Instagram account, the Hyperfine, that I somewhat participate in, but you can come say hi there.
You can, okay.
I was going to say, I'm personally like Tortilla on Instagram.
You can tweet me, I suppose. I've almost never used Twitter, but it's my handle is PhysZaks, and that's PHYZAKS, PhysZaks.
Yeah. I'm also like Tortilla on Twitter. So it's Derek Padilla like Tortilla, Instagram and Twitter. I tend to avoid Twitter, and unfortunately, we're recording this like January 23rd. Unfortunately, come politics time, I do venture back into Twitter to see things, and I don't know, whatever, self-masochism of torturing myself by paying attention to what's happening politically. So, yeah. So I come and go from Twitter. But yeah, you can hit me up, and I'll get the notification and say hi.
All right. Well, thanks for listening, everyone, and catch us next time. I don't want to give a time.
No
frame.
exact dates. It's coming some point later, some point in the future arrow of time.